Okay, so now we're going to look at a second example of computing likelihoods, and this time we're going to look at a situation where data is continuous rather than discrete. So that's the second link here, likelihood ratio simple continuous data. I click on that. Okay, I hope you can see that. So remember that the likelihood ratio for two models is defined as the probability of the data under model 1 divided by the probability of the data under model 0. So that's nice and easy if the data are discrete because the probabilities are well defined. What happens now if instead of discrete data, we have continuous data? Well, the short answer is that we can simply replace the probabilities in the likelihood ratio or the probability mass functions that we would use for discrete data. We just replace those with the density functions. So in other words, we have continuous data, so we're going to have a probability density function for the data under each of the models. That's P of X given M1 and P of X given M0 in this second expression here. So we just, instead of using the probability mass function, which we'd use if they were discrete data, we just use the probability density function. So I'll give you an example of this, and then I'll talk a little bit briefly about why this is a sensible thing to do and how to think about this maybe. but before I, one thing you could just take away from this is I just use densities instead of mass functions, but maybe you ought to be thinking about why, and we'll come back to that in a minute. Okay, so before we do that, let's take a look at this example. So this example, where you're asked to imagine trying to screen people for a disease based on measuring the concentration of a protein in the blood. So this is X is going to be the level of the protein in the blood, and I'm going to imagine that X has a kind of a continuous distribution. And in particular, I'm going to assume it has a gamma distribution. So in the picture there, the black line shows a gamma distribution with mean 1 and shape 2. So that's the distribution for the normal individuals, if you like. And then in diseased individuals, the protein tends to be elevated. So it has a gamma distribution with a larger mean, and that's the red line there. So those are the two models, if you like, that we're trying to compare. We've got the disease model and the normal model. And then given a data observation, we're going to ask the question, well, do the data support the individual being diseased or normal? And we're going to measure that using a likelihood ratio. So let's suppose that the observation that we have is, here we go, 4.02. We observe 4.02 for a particular patient. What's the support from the data for being diseased versus not diseased? So if you look at the graph, just around 4 there on the x-axis, you can see that the red line is appreciably higher than the black line. And the intuition is that therefore the likelihood ratio is going to be in favor of the disease hypothesis. So if we compute, in this case, I've computed the likelihood ratio in favor of the normal hypothesis, I get a ratio of those two densities, that's the black density divided by the red density, and that ends up being 0.07, or if I reverse that, it's roughly 14 to 1 in favor of the disease model. That is, the red line is 14 times higher than the black line around there. So the likelihood ratio is roughly 14. So if we saw those data, we would say the data favor the disease model by a factor of 14. Or in other words, the likelihood ratio for the disease model versus the normal model is 14. Okay, so why is it okay to just use the densities? Well, some people just define the likelihood ratio in terms of the densities, but I would prefer to think about this in terms of defining things in terms of probabilities, and then deriving what the answer should be for continuous distributions. And that's just because sometimes this actually this way of thinking can break down. So sometimes densities can get kind of ill-behaved in some models. Unlike, you know, probabilities have to be between 0 and 1, but densities can be kind of arbitrarily large and kind of go off to infinity even for some distributions. So it's a good idea to have an understanding of what kinds of assumptions we're making here when we use that, plug that density into a likelihood ratio. So the way I like to think about this is that when I see a concentration of 4.02, I didn't really observe it to be exactly 4.02. There's probably some kind of level of precision associated with that measurement. So maybe it would be reasonable to think that actually the protein level actually lies somewhere between 4.015 and 4.025, just because it was given to 2 decimal places. If we know more about the measurement precision, maybe we could you know, be more formal about this, but just let's assume that the reason it was reported as 4.02 is because it lies somewhere between 4.015 and 4.025. And so to the nearest 2 decimal places, it's 4.02. So then now you've got actually you've got a discrete observation, right? If you've got an event that X lies in that interval, which you can assign a probability. And of course, that probability is the integral of the probability density function between those 2 points. And provided that the density is well behaved near 4.02, which in our example we can see it is near 4, the density is nice and well behaved, you can see that the integral under the red line just near 4 will be roughly equal to the height of the red line at that point times some small bin width. And the same for the black line. And so the ratio of those 2 areas, the ratio of those 2 probabilities, will actually be the same as the ratio of those 2 densities. So in other words, as you let, essentially, if you want to be more formal about it, as you let the epsilon, the measurement precision, go to 0, the likelihood ratio for that event, as defined using discrete probabilities, will converge to the ratio of those densities. And I'm not going to go into details, but there's a little example here to show where that approximation may break down. So most of the time, it's just fine to plug densities into likelihoods and use densities instead of probability mass functions when you're working with continuous data. But this essentially explains why that's okay. And I think it's a good idea to understand what's going on underneath the hood that when you're doing that, and to be a bit careful if you do see densities that are going off to infinity, for example.